So we're going to learn a new chapter of this class. It's about the drinking water treatment. So a lot of people also call this as the water treatment, okay? Because we deal with this drinking water for most of the time. I mean, for the wastewater, the difference is that wastewater treatment is not called as water treatment, okay? So whenever people mention about water treatment, it's specifically about drinking water, okay? So I think it's mainly because we have been spending most of the time as human to treat drinking water. Right? Wastewater is probably just a topic of the last few decades. It's still a new topic. So this is going to be chapter 10 of your textbook. So I think it will be good to go over the textbook as well. So again, if we do a recap of our last class. So last class, we gave, I think, one simple example about how to use the DO sag curve, right? So basically, with this equation here, we can, why is it not working? Yeah, with this equation here, we can predict what is the oxygen deficit or the dissolved oxygen at any time. So we can find out where the water quality is the worst, right? And then we also mentioned that for the river water quality management, if you want to do calculation or if you want to do sampling, people normally use the late summer condition to do their experiments or to do their calculation, mainly because the condition in late summer is going to be the worst, right? The water flow is going to be the lowest, the oxygen or the dissolved oxygen concentration is also going to be the lowest. So at the end, we discussed what is the water quality in other water resources like lakes, estuaries, and ocean. Right? So for lakes and estuaries, the major problem is the algae bloom. Basically, you're generating too much of the biomass, and once they die off, they're going to consume all of the oxygen, right? So specifically, we mentioned about the dead zone, which is the area of the Mississippi River when it mixes with the, I would say, the Atlantic Ocean, right? So you get this mixing of the water, and because it has so much of biomass inside, it's going to deplete the oxygen in the water. So for the ocean, a major problem is the climate change because the seawater is getting warmer and warmer. It's going to damage a lot of the living organisms. So this chapter, we're going to learn about the more practical problem, right? It's about the drinking water or the water treatment. So to understand this treatment, we need to first know where our water is coming from. I think we explained that in our earlier chapters. So basically, our water can come from deep wells. So those are underground water, right? And if you consider the water quality in the deep wells, actually, most of the time they're very clean because there are no living organisms inside. It's deep down in the ground, right? You don't have any sunlight exposure. You don't have any nutrients inside. So the living organisms won't be there. So they're relatively clean. So the major problem is the hardness of the water because there are too much rocks inside, right? So basically, let's say this is the ground and then water can be flowing here, but you have a lot of rocks in here or minerals. So these minerals can dissolve these calcium ions and magnesium ions inside, right? So we know that the rocks are mainly composed of calcium carbonate or magnesium carbonate. So what happens is, since you have water flowing by, because of the solubility of all these solids, you can get calcium bicarbonates, right, or magnesium bicarbonates. So the thing is, once these, basically these salts, they are soluble. They're very soluble in water. So what happens is these salts can get delivered into the households and once you use your kettle or use the bathtub, whenever it gets to a higher temperature, these things will turn back into rocks. Okay. So that's why you can see the white scales on the faucet, and also at the bottom of the boiler or the kettle. So mainly we call this as the hardness of the water. Right? So for underground water, normally it's quite clean, but the hardness is a major problem. But I would say that the underground water is not commonly used. So if you just break down all the water usage in the United States, you can see that most of the water is actually coming from the surface water. Okay, it can come from the shallow wells, it can come from the rivers, lakes, and reservoirs. Right. So for these surface water, it's going to be a little bit more complicated because a lot of living organisms can stay in there, right? So you have pathogens, you have plants, you have fish. So generally, the water here is going to be more polluted, and that will need more treatment. Okay, so in this class, we're going to mainly focus on the treatment of the surface water. So maybe next class or next week, next Wednesday, we're going to talk about the hardness. So there are a series of reasons why we want to treat the water quality. It can come from all aspects, for example, the appearance, right? The color, odor, turbidity, or solids. We don't want to drink any water that has suspended solids inside, right? And then there are pathogens because of the living organisms. There are bacteria, viruses. Some organic pollutants can also be there. For example, the pesticides or fertilizers, right? And there can be inorganic pollutants as well. You have lead, arsenic, and some other heavy metals. They can get dissolved into the water. And disinfectants and disinfection byproducts. So actually, they should belong to these organic pollutants here. Okay, so there are different types of these pollutants. And finally, you have the radionuclides, which are radioactive. If people ingest them into the body, then it's going to cause maybe cancer from the polluted water, right? So because of that, people have to set up standards, okay? So you have to regulate what is the maximum concentration that people can take, or basically send these regulations to the water treatment facilities saying that you have to satisfy this regulation, okay? The concentration have to be below certain level for these pollutants. So there are two types of standards. So one is the maximum contaminant level, or the MCL. So these standards are specifically designed for pollutants that we know is definitely going to harm the human health. Okay, so for example, the lead, arsenic, right? Because of these heavy metals, they can get accumulated in human body. It's going to harm the health. So that's why we have to set up clearly what is the MCL. So these are enforceable, and it's for regulated substances. But at the same time, there can be some species that people are still unclear about this toxicity. For example, some organics or disinfection byproducts, okay? So they're relatively new. There haven't been enough of experiments on that. They can be chronic effects, right? After, say, 20 years, then people start to show some of these diseases associated with the pollutant. Then it's still hard to say. So people also design these MCL goals, so maximum concentration level goal. So these are designed for the pollutants that we're still not sure about. Okay, so the MCL is the things that definitely going to cause the harm. MCLG is the species that we're still not clear about. So I guess maybe many of you are living off campus. Okay, so if you rent an apartment, rent a house, you gotta deal with the RMU. Okay. So on their website, although I think it's quite old website, it's a pretty old website, they actually can show you these consumer confidence report. Okay. So if you're interested, you can click in, and then they give out these definitions of different terms. So basically, it's the conditions in Rolla, and also the basically trying to educate the general public, right? You see that they have definition of MCL and MCLG. So they have reports for every year, right? And then if you click one of the report, they actually provide you what is the concentration of these pollutants before they deliver into the households. Okay, so for example, they measure copper, lead, right? Chromium, and some disinfection byproducts. Okay, so they have the range or the maximum, the lowest, or the minimum values. So actually, their website is quite informative if you're trying to understand what is the water quality in Rolla generally. Okay. So these are the standards. So we know that pollutants are harmful. We set up standards, and now it's just a question of how to remove these pollutants. Okay, how can engineers come up with devices to get rid of these things? So here I'm just going to throw out all the terminologies, right? So later on we can go over it one by one, and also we want to pay attention to what should be the correct sequence of all of these treatment processes, right? You don't want to, let's say, first filter out all the small particles and then realize that, oh, well, there are some reactions or the process that can generate more particles. And then you have to go over the filtration again. So you don't want to create these duplicated processes. So I'll just introduce it one by one. So first is about the microorganisms, like the pathogens, bacteria, viruses. So people use the disinfection to deal with the problem. I would say that most of the countries are using the chlorination to deal with the microorganisms. And that's why when we go to the swimming pool, we can smell that chlorine smell, right? So it's very effective and very cheap to deal with the pathogens. So here, what I'm showing is the, I don't know if that's clear enough. Let me zoom in, okay. So this is the death rate for one type of disease called typhoid fever in the United States, starting from 1900 to 1960. So you can see that at the year of around 1908 or 1909, the United States started to reinforce all of these chlorination setups. Okay, so what you can observe is this exponential decrease of the death rate from this disease. Okay, so this is associated with the pathogen in the drinking water. You can see the chlorination is very effective in protecting people's health. Okay, but these microorganisms are not the only one pollutant, as we introduced earlier, right? So there can be larger debris. For example, the wood chunks, right? So for example, tall grass, when they die off, you can have these larger debris, right? You can have, for example, fish, right, in the river. We have to block them out. So that can be quite simply done by screening. Just put a mesh in there to screen it out. There can be heavy particles, for example, the sand particles or the soil particles. If they're large enough, you just let it settle down. Let's say wait for maybe 1 or 2 days, they can settle down onto the surface. So the type of thing, pollutants that's quite difficult to solve is called the colloid. Okay, so what colloid means is generally they're very small particles of maybe 1 micron or below 1 micrometer. So if you calculate the gravity, these particles are very, very small. Let's say in the water, they're very, very small. So the gravity is very small. So even you set it up there for infinite long time, let's say 10 years, 100 years, they're never going to settle down. They will just stay suspended in the water, okay? So an easy analogy can be milk, right? So the milk shows a white color, right? It's because of the proteins inside. So these proteins are pretty large, but there's no way that the protein can settle down, right? Even after staying, let's say, put it there for 1 year, 10 years, they're not going to settle down to the bottom of the water. So because of that, we have to come up with some chemical methods to deal with that. So we specifically call this as the coagulation and flocculation method. Okay, so the coagulation What coagulation means is we're adding in some species called coagulants. Okay, so generally they are aluminum ion or ferric ion. Okay, so once we add these ions or salts, for example, the aluminum chloride or ferric chloride, so once we add them into the water, they're going to cause these suspended solids, suspended particles to get together, to bombard each other. Okay, they're going to collide with each other to make it larger. Okay, so they can be larger particles like have the shape like this. And then the flocculation means these larger particles can further collide with each other. Okay, to form something like this. Okay, so we call this specifically as flocks. So once you form flocks, they're going to be large enough so that they can settle down. And for the smaller flocks, we can use the typical filtration to remove them. So that's why the coagulation flocculation is very effective in removing the colloids in the water. So it's also a part of the contents we're going to learn later on. So as I said, for small particles, for example, the smaller flocks or the, let's say the smaller sand particles, we can use the sand filtration. We just build up a, let's say a container filled with sand, and then let the water flush by. Right? The sand are going to have a smaller space in between, and then you can remove those smaller particles. So specifically for underground water or the groundwater, we're going to deal with the hardness, let's say the magnesium or calcium ions by softening the water. All right. So finally, if there are some dissolved organics, say odors or some other species, we can use some more advanced methods. For example, the advanced carbon adsorption or air striking to remove these. Okay. So these are the general methods that people can use to treat the drinking water quality. But we need to think about what should be the correct sequence. Okay. So here, what I'm showing is a schematic diagram of a water treatment plant. Okay, so we can go over them one by one. So basically, this plant is taking water from a lake, right? And this is the intake pipe. So we have the preliminary treatment by just setting up a bar screen. So basically, these will remove the larger chunks of wood or fish or grass from the water so that we can deal with cleaner water. So there's another screen here, and then we use some pumps to lift it up. So basically to create a potential energy so the water can flow down or flow along the pipes, right? So here we have the first step, which is the pre-chlorination. This is going to kill a portion of the pathogens in the water, okay? So after this disinfection or this pre-disinfection, pre-chlorination, we're going to send them into the coagulation and flocculation setup, okay? So first, basically here we're going to introduce some flocculants, right? And let the particles to collide with each other. And then in the flocculation, they're going to further collide to form larger flocks, right? And then we'll send them into a sedimentation basin. So basically here, it's just a gravitational settling of these larger particles. So we're going to get further cleaner water from here, and then we send them through the sand filtration to remove smaller particles, okay? So after that, we have the post-chlorination to boost up the chlorine concentration. So basically at each household, we're still having some chlorine level, right? To make sure that there are no pathogens inside. And I think more and more water treatment facilities are adding this fluoridation setup because basically for very young children, when they're developing their teeth to prevent the cavity or tooth decay, you need to have fluoride inside. Okay, so they're adding this as well. And then this is the second pump. Right? So we have this low lift pump, and we have this high lift pump. So high lift pump is going to pump the water into the water tower. Or for some area, when they don't have the water tower, they can just directly send the water into different households. Okay, so this is a ground level reservoir. Right? So this is the general sequence. So now if I ask you, should we put the sand tube filtration up here, right, at the beginning? It is not practical, right? Although we can remove larger particles, we remove smaller particles, but we're forming coagulants, right? We're forming, basically we're forming more particles during this coagulation method, right? We're forming flocks. Basically, those are particles again, right? So if these, if the sand filtration is at the beginning, then we're forming particles and there's no way we can remove them anymore. Okay, so the sand filtration is generally, basically sand filtration have to be following this coagulation, flocculation method. It cannot be before, because here we're generating particles. Right? So this is a general flow chart. So I think for a lot of newer water treatment facilities, they're going to use a little bit different, different methods. So for example, they may just forget about the pre-chlorination. They may completely move this chlorination to the downstream after everything is dealt with. Or they can change the chlorination into a UV disinfection. You can just shine UV light to remove the pathogen, or to kill the pathogens. So now we can go over them, or go over these steps actually from the coagulation and flocculation method. Okay, so here, everything is quite simple here. So in terms of the coagulation and flocculation, as I said, we're mainly trying to remove the colloids. Okay, so colloids are suspended particles in the water, and there's no way they can settle down. So the example can be milk. So the milk is just a colloid that contains a lot of proteins inside. So similarly, if you can take the raw river water, they're going to show some color like this, gray color or brown color. So the thing that's creating the color is also colloid, right? So because of that, we know there's no way that they can settle down. We'll have to deal with it differently. So as I said, one reason is that the colloid particle is too small. Okay, so if they're below 1 micron, let's say, or I should say 1 to 10 micrometer. So their gravity is too small, and it's very difficult for them to settle down. But there are 2 more reasons why they're very stable in the water. So this is the first one. So the second one is for the river water, because of the, let's say the surface chemistry, let's say if this is a very small particle, because of the surface chemistry, these particles tend to have negative charge. Okay, I think this is related to the soil composition or the sand composition that's giving them this negative charge, or they can carry multiple negative charge when they're put into the water. Okay, so because all of these particles are similarly charged, so all of them are negatively charged, they're going to repulse each other, or dislike each other. So it's going to be very difficult for them to collide and then form larger particles. So basically, they're always moving, but they're repulsing each other, right? And then the third reason is that for these very small particles, they have a motion that's called the Brownian motion. So basically, what happens is you have water molecules surrounding it, right? So the size of these particles is not significantly larger than the water molecule. So what that means is, while the water molecule collides with the particle with a random direction, so these particles are also going to move with a random direction, okay? So this random motion is called the Brownian motion. So because of these 3 reasons, so basically one thing is very small, they cannot settle down, and then the particles are repulsing each other, and further these particles move randomly, so always moving randomly. So because of these 3 reasons, it's going to be very difficult to remove these suspended solids, and that's why the the colloid is also very stable. So the method we can use is to introduce the coagulants into the water. All right. So if you consider if all of these particles carry negative charge, so an easier way to let them collide with each other is to introduce positive charge, right? And actually, the more positive charge you can introduce, the more efficient this coagulation will be. So that's why people would put in aluminum ion or ferric ion inside, right? So that they can pull these negatively charged particles together and also let them to coagulate with each other. So basically what we do is we're neutralizing the surface charge. And then when the particles are getting in contact with each other, they form this van der Waals force, and it's difficult to break them apart anymore. And then they're going to form these larger set level particles, right? So actually, as I said, these particles tend to carry negative charge, but the actual situation is that it's a little bit more complicated than that. Okay, so the particles carry a negative charge, but in the water, what happens is there's going to be a layer of positive charge surrounding the particle. This kind of makes sense, right? We know that in water, there are a lot of positive and negative ions, right? So if you put in a negatively charged particle, then those positively charged ions are going to surround this particle here, okay? So we call this layer as the rigid layer or the stern layer, right? So you don't have to memorize these. I'm just trying to introduce some general concepts here, okay? So because of this stern layer, what's happening is that it's going to create a net positive charge for this composite here, okay? So if you just count what is the charge within the particle and in this stern layer, they're going to carry a positive charge. But because they carry a positive charge, again, they're going to form another layer surrounding it. This is called the diffused layer. So for this layer, you're going to have a net negative charge, okay? But still adding all of these layers together with the particle, they're going to carry a negative charge, okay? So basically, although we're forming multiple layers surrounding the particle, we're not affecting the overall charge of the particle. And that's why it can still remain stable in the water, right? Carry a net negative charge. So as I said, these coagulants can be these ions that have more positive, basically positive charge, right? So this is what this plot is showing is that we can introduce actually different types of ions. We can introduce aluminum ion or calcium ion or sodium ion. So what this is showing is that if we use them as the coagulants, so the x-axis is dosage of coagulants, then the y-axis is the residual turbidity. So just trying to show how turbid this water is or how dirty this water is, right? So everything starts with 100%. And then you see that for the aluminum ion, the turbidity dropped down very quickly at a smaller amount of the dosage. But for these ions, doubly charged or singly charged ions, you have to put in more dosage to remove the turbidity, right? So that's why we prefer these, let's say, polyvalently charged particles, or charged ions, right? Aluminum ion or ferric ion. Basically, the more ion or the more charge it can carry, the more effective this coagulant will be. So here it's showing another type of coagulant. So this is an organic coagulant. What happens is that it's also quite effective. Okay, so you see the turbidity drop down from 100% and then drop down to 0, right? But what happens is if we put in more of these coagulant, then basically you're overcharging the particles. Okay, so they're going to carry positive charge again. What happens is that turbidity is going to increase back to 100%. So it's going to be very difficult to control what is the dosage you put into the water, okay? But these metal ions, or especially these two ions, are very, very effective to deal with the colloids in the water. So further, we can learn a little bit more about these coagulants. So for example, for the aluminum ion, what we introduced is actually aluminum sulfate. So this is also called alum. Okay, so this is a type of mineral that we can get from the rocks. So what happens in the water is that these aluminum ions are going to react with water to form aluminum hydroxide and hydrogen ion. Okay, so inside the, actually what is binding all of those colloids together is the aluminum hydroxide. Okay, so because it is sedimentation, you can collide with all the particles and then bind them together to form coagulation and the flux. Okay, so because of that, as you see, so in this chemical process here, if we are putting in the aluminum ion into the water, we're actually generating hydrogen ions. So what that means is the more coagulant we put in, it's going to be more acidic, right? And then let's think about what should be the typical range or the best range to do this reaction here. So if you want to pull more, or if you want to let more of this reaction to happen, then you should think of a way to remove these hydrogen ions, right? So that's why for the coagulants, the higher the pH, the better the coagulation and flocculation. So basically, you're creating some incentives to remove these hydrogen ions by the OH ion, right? So the higher the pH, basically the more effective for the reaction that's going this way, right? So basically, we can dissolve more aluminum ion, and then we can form larger flux. Okay, so does that make sense here? Okay. So there's a best pH range that's from 4.5 to 8 in terms of the water pH here. But if it's outside the pH, we need to think of a way to tune it first into this best range. Okay. And in terms of the ferric ion, we can introduce ferric sulfate and ferric chloride. So it's very similar to the aluminum ion. It's going to react with water and form ferric hydroxide. So the advantage for the ferric ion is that it can have a wider range of the pH, 4 to 12. And then you can have a better control of the flocculation. So apart from these coagulants, there are also aids for coagulation. So if you think about the process, basically we're letting these very small particles to collide with each other to form larger particles, right? You have these very small particles, they collide to form these particles, and further they will form these flux. Basically, they're going to have this chain structure and also a larger area. Okay, so if we want to let these larger flux to settle down, then what we can do is we can actually introduce more particles in the water. Let's just throw in more activated silica and clay. So what happens is that if you have these larger particles inside, and then they're going to further collide with the flux, and then let them settle down faster, right? And also because these silica and clay, they are larger particles, they can settle down no matter whether they collide with the flux or not, right? So it's like in the air, if we just have a rain down, right? Have a very strong rainfall, then it's going to remove the suspended particles in the air. So the air is going to get more clear. So it's a similar mechanism. We just throw in larger particles to let them collide with the flux, and then let this flux to settle down faster, right? And then we can also introduce alkalinity to adjust the pH. Right? As we said, we want to tune the pH into a little bit more basic, right? To let them react with the hydrogen ions so that the reaction is going this way. Right, so that's why we need alkalinity to neutralize the acidity. We can use lime and soda ash. Okay. So if you see where this coagulation is taking place, they're actually happening here. Okay, so after this pre-chlorination, you introduce the coagulants in here. right? And now let's think about it. So basically, we're throwing in some chemicals in here, right? So do you prefer a faster mixing of these chemicals with the water, or you prefer slower mixing? So let's think about it, okay? Or just take a direct guess. Just raise your hand if you feel that we should use a slower mixing or faster mixing. Yeah, I see a few, right? So we should use a faster mixing, because if it's slow, then they might just settle down in here, right? So that's why in the coagulation process, what we prefer is that we want a turbine or want a blade that can rotate very fast, okay? So that's why we need to have a rapid mix of the coagulant, okay? So we use these turbines or paddles that can have, or that can create a very, very fast speed. And because of this fast speed, the residence time of water in this rapid mixing is also pretty short, okay? So people will use the degree of mixing or the velocity gradient to describe how fast the mixing is. So basically, the velocity gradient is calculated by dv divided by dx. So basically, it's the velocity that's at the edge divided by the radius, okay? So it's calculated by v divided by r, right? So this is the velocity gradient. So for this rapid mixing process, people will use the mechanical mixers. So what they find is that when the velocity gradient is 700 to 1000 per second, it is the best, okay? So this number doesn't look very large here, but if you just think about a scenario, let's say the blade here we have is 1 meter. So 1 meter is not a very long distance. It's like this long, right? But if you plug in this equation here with 1 meter, and this equal to 1000 per second, you can find that the velocity at the edge is 1000 meter per second, or 1 kilometer per second. This is a very, very large speed, okay? So that's why we need to use some very high power turbines to basically mix the coagulants better with the water. So this can suspend the coagulants within the river water or the treated water, so that we can get a better coagulation effect, okay? So normally this coagulation time within this process is also pretty short. It's just 20 to 60 seconds, because what we want to make sure is that if we let it coagulate for too long, then what happens is if you form these smaller particles, and then what they try to do is that we want to form these larger flocks, right? But if they form these larger flocks here, and because of the fast speed of the turbine, they're going to break these flocks into smaller particles again, okay, because of this stronger mechanical mixing. If we let the coagulated particles to stay for a very long time in the coagulation process, we may not form the flocks. So that's why normally we will use a smaller retention time, right, 20 to 60 seconds, and then we're going to send them into the flocculation process, right? So I think for this chapter, normally you can find problems like, if you know what is the retention time, if you know what is the flow rate of the water, then what is the volume of the reactor, okay? So we can just use this simple equation. So the flow rate multiplied by time is going to be the volume of the reactor, okay? So basically this is a rule of thumb for the design for different, let's say, coagulation or flocculation devices. If you know the time, normally we'll designate a retention time. And then if you know the flow rate, we just multiply together to get the reactor volume, all right? So these are different types of the coagulation reactor, right? You can have the single turbines here. You can have double or basically you want to achieve a very fast speed so that you can suspend the coagulants in the water. And then we get to the flocculation process. So as we said, to form these flocks, we need a more gentle environment so that these smaller particles or the coagulated particles can further collide with each other to form the larger flocks, right? So to form something like this. And then because of that, we want a smaller or a more gentle mixing. So here, people normally use the paddle flocculators or baffled channels. Okay, so paddled flocculators are still going to be a turbine that looks like this. Okay, so you have a shaft in the middle, and then it's going to stir the water, right? But if you compare what is the velocity gradient, 30 to 60 per second, and compare that to the coagulation process, right? This is much, much smaller than the coagulation because we want a more gentle environment to form flocks, right? And then because of that, we also want a larger residence time in the flocculation process so that these particles can stay longer, right? And they can use their time to form these larger particles so that they can settle down onto the bottom, right? So because of that, you can see that, let's say the flow rate, again, the volume is equal to flow rate multiplied by time, right? So the flow rate through the coagulator and through the flocculation or the flocculator, right? They're going to be the same. It's just a single channel coming in here, going out here, right? And then the thing that determines the volume is just going to be the retention time, right? So the retention time for the flocculator is 15 to 45 minutes, and the retention time for the coagulator is 20 to 60 seconds. So because of that, the volume for the flocculator is going to be much larger than the volume of the coagulator, right? So that's why in this diagram here, you can see that flocculation is going to occupy more space compared to the coagulator here, right? So this is a, let's say, a paddled flocculator, right? So we can also have designs like these so that you have this rotation and horizontally, right? So they can mix better and then stay for a longer time and then come out. So these are going to use, still going to use a, let's say, a turbine, or at least let it rotate, right? So we can design something that doesn't use that energy, doesn't use that rotation. So what happens is we can design these hydraulic flocculator or this baffled channels, right? So what happens is that we can introduce the water from a higher location, and then because the water wants to drop down, right? The outlet is here. So what happens is that water wants to come down here. But because you have these channels here, so they have to go over all of these channels again and again and again and again, and then come out here. So in this way, we can guarantee a long retention time. Okay. They can stay longer in this gentle environment. They can form larger flocks. So the same thing here. Basically, we introduce the water from the coagulator, and then we also pull off the water from here. Okay, so because we have these channels, the water can only go again and again around these, right? So in this way, you can guarantee a longer retention time in the flocculator so that you can settle down more particles. Okay. So now I have a quiz question here. So compared to the coagulation, why a velocity gradient? Why a smaller g is being used for flocculation? So I gave 3 options here. Let me see if I can get the Zoom participant to choose this too. So just think about it. I'll give you half a minute. Okay, we'll stop here. So I'll go with the face-to-face students. So is it A to, let's go in this way. Okay. So anyone choosing A to destabilize particles? What about B? All right, okay. So it's not to save energy. Okay, so I think we're getting the similar response here. So the correct answer should be B, right? We want to create a more gentle environment so that they don't break up the flux, right? Okay. So people can also design these things called the clarifier. Okay, so the clarifier is going to be a more centralized way to deal with the water quality. So what happens is we can just directly send in the water from the left here. And then what happens is we can send in the coagulants from the top. And then here we can have a turbine that rotates at a very fast speed, right, to quickly suspend the coagulants into the water. And also because you have a smaller volume here, so the mixing is going to be more complete. Okay, so further down here, we can use a, like, let's say a paddle with a much smaller speed. So what happens is that you can guarantee the mixing is more gentle. And then within this water body here, they're going to settle for a longer time. Okay, so during the real application of this clarifier, so the water level is going to be much higher. It's going to be here. Okay, so all of this space is just water. Okay, so what happens is water is going to untreated water come in this way, coagulation, flocculation, and then settling and all the way going up, right? And then you get more clear water here. And then the effluent is going to be the treated water. So this is achieving all the goals into one setup, right? So that's why we're having the mixing, flocculation, clarification in the same tank here. And that's why if you go to some modern water treatment facility, you can see these round things here, okay? So basically these will achieve the water treatment in just one setup. And actually in wastewater treatment facilities, people also use this clarifier, but it's a little bit more simple compared to the water treatment, okay? So if you see, after the coagulation and flocculation, we're going to send these larger particles into, or the treated water into the sedimentation. So inside the sedimentation basin, what happens is that larger particles are going to settle down, right? So let's say this is a larger particle, they're going to settle down. If you have a further larger particles, they can settle down earlier, right? But for very small particles, there's no way for them to settle down. And actually, at the end, there's a flow that's going up. So basically, anything that cannot reach to this point, any particle that cannot reach to this basin here, they're going to flush up and then exit the sedimentation basin, okay? So that's why there exists a critical velocity, let's say a settling velocity, okay? So if the settling velocity is much larger than this critical velocity, let's say V is larger than V0, it means that these particles can settle down. Well, if the settling velocity is below this critical velocity, then they can come out and still flow, basically escape this sedimentation basin, right? So for the sedimentation basin, we call this critical velocity as the overflow rate, okay? Let me just write it down. Velocity. So basically, we can calculate what is this critical velocity just based on the dimension of this sedimentation basin here. So we're going to talk about this in our next class. And then, so for this time, the homework, I think it has a few problems about the water hardness. So you don't have to work on those for now. So we'll cover that in our Wednesday lecture. All right. So that's all for this class, and thank you for your attention.